All attendees are in listen-only mode.
Good morning, everybody, and thank you for attending our webinar today. Today's topic is going to be playing off the last webinar, and we're going to talk about touch current testing, and this is 102. If you didn't attend the last webinar, which you may guess is touch current testing 101, I do highly encourage you to go back, go to our website, go to the webinar archive, and watch it. It's free. You can watch it at any time. It's right about an hour long, as this one will be. And it is very helpful in kind of building on materials. So just a quick recap of what we talked about last time. We're going to go over that in a second because I do want to give people a feel for what we covered. And then we will go over the outline of what we're going to talk about today, which is definitely more finely honed and a little more specific than what we talked about last time, which was a little more broad with regards to leakage current. So we talked about not just the leakage current, but touch current and earth leakage and things of that nature. A couple notes here before we get into it. If you do have questions, thoughts, things of this nature, or you're having problems with the webinar itself, use the utilities that you have there in the go-to bar. You're going to notice a chat utility. So if you're having any issues with regards to the webinar itself, you lose my audio or it seems to be a delay, something lagging, address those to Jim Kennedy through the chat line. He is our host and he will be able to help you with that. If you have any questions with regards to the material itself, we have Pete Stevens, our domestic sales manager, helping us out today. He's very knowledgeable and he can certainly help answer some of those questions. So throw those out to Pete or the group and we can help you with those as we go through the webinar as well. Any questions that we feel would be pertinent to talk about as a group, Pete will usually address those to me after the webinar is done. So I usually like to try to leave about 10 minutes or so, or 5 or 10 minutes to leave it open to questions. And as always, there are certain questions that just are far too in-depth to cover in this single webinar. If that does happen, you can always email us directly and would be more than happy to talk about it more in depth, go through the standard, talk about your equipment, whatever the case might be. We're always available for application support and just general questions and discussion. So email us on that front. We'll have some email information at the very end of the webinar, so just keep that in mind. If you want a copy of this presentation, we can send the slides to you. Just contact Jim, Jim K at AS Research, and he can send those off to you. And this webinar will be available in a few days on our webinar archive, just as all of our webinars are. So, notes aside, and that being said, let's get started. Now, to quickly recap, Touch Current Testing 101, what did we talk about? We talked about some basic safety stuff, primarily shock hazards, because why do we do a leakage current test? Well, we do it to mitigate shock hazards. It's what the safety standards call out for. You look at the section in the safety standard and it's shock hazard, and these are the tests that you run in order to avoid shock hazards. Obviously, it's not just the leakage test, but that's what we're talking about here today. And then we got into leakage current. What is it? Insulation barriers, things of that nature. So as I mentioned before, it was a lot more general than what we're going to be talking about here today. We did briefly touch on what touch current is, types of touch current, and how it's measured. And I'm actually going to cover that a little bit again today because a bit of a refresher can't hurt. I also have some model circuit diagrams to kind of show you guys. And then we did some video demonstrations that talked about standards and how they talk about leakage current and how it's supposed to be run. So again, if you didn't see touch current testing 101, this one might be a little tough to follow unless you've done these types of tests before, in which case you'll have no problems jumping right in. I do highly encourage you to watch it. If you've never been exposed to touch current testing before and you're jumping in right now, you may want to, after you go through this one, go back and watch that one and then rewatch parts of this one. Because as you will see in the next slide, we are going to be really getting into it a little more heavy duty this time around. And this particular webinar really is a lot more focused on medical device testing because it deals with patient leakage. Now granted, touch current applies to many standards. Patient leakage, I suppose, could apply to other standards as well, but really we're talking about the 60601 medical device standard, the Dash 1 standard, the main general requirements for testing. I'm not going to delve into the Dash 2s or the substandards or anything along those lines in this particular webinar. We simply do not have the time for something like that. So we're going to first talk about the leakage current types. Once again, I want to cover touch current. We're also going to talk about patient leakage, patient auxiliary leakage, and then mains on applied part leakage. We actually got several inquiries during the last webinar about mains on applied part, and I kind of told everybody to just hold that thought until the next webinar, and we're going to talk about it a bit today. I do also want to talk about leakage current in general. I just want to make sure that we're all on the same page with regards to leakage current and the networking and the measuring devices used for leakage current measurements. Obviously, you can't talk about patient leakage without talking about 60601, 3rd edition, and we're specifically going to get into Chapter 8 for the leakage current tests of that standard, even more specifically starting at Section 8.7. I'm sorry, it goes even before that. I believe 8.6, we're even talking about just the leakage current tests in general. So along with that, well, it's good to talk about what the standards say and get everybody a feel for how these measurements are made. I think just as important are showing actual testing examples, because I have a feeling that many of the people who are attending this webinar, you've seen the standard, you know what it says, and you have an idea for what needs to be done. So me just talking about the standard all day might not help you all that much. So what I did was I recorded a series of videos of me actually running touch current tests, patient auxiliary leakage, and then I have a video at the end that does a automated mains on applied part voltage test. It's kind of a little bit of a longer video, so I want to try to leave enough time to show the entire video. I think it's a helpful video. Obviously, we'll be using our equipment, more specifically our Omnia all-in-one tester, but I'm really only using the leakage function for these videos, and you'll see that as we move through the material. But in the last couple of years, we've done a lot of these leakage testing videos, and we got very positive responses, so we want to keep that up. So that being said, let's dive in, since we have quite a bit to cover here today in a short period of time. So if we're going to be talking about these leakage currents, we need to talk about the types, and let's define them a little bit here. So touch current. What is it? It's basically electrical current through the human body when it touches one or more accessible parts of an installation or of equipment. This is also known as enclosure leakage current, i.e., if I were to walk up and touch a piece of equipment with my hand while it's running, what kind of current am I going to be exposed to? Not only what kind of current am I going to be exposed to, but what if we have various things happen, fault conditions as we call them, like the interruption of a conductor, the interruption of a protective conductor, the reversal of a polarity, maybe the shorting of an insulation barrier. These are what we call fault conditions. So we're going to look at this and measure these types of currents under these varying fault conditions. It's kind of what we talked about last time as well. Leakage current, just in general, is what I like to call our worst case scenario measurements. So again, I'm calling it touch current throughout this webinar, but it's also called enclosure leakage. You may have heard that used instead. Patient leakage current is kind of specific to patient connections. So it's current flowing from patient connections via the patient to earth. It's current originating from an unattended appearance of voltage on an external source on the patient and flowing from the patient via the patient connection of an F-type applied part to earth. That was a lot of words. Sounds confusing. This relates specifically to F-type applied parts, which I'll get into in a little bit. Basically, what that's saying is, and these are two separate definitions, what that's saying is if you have a patient lead that's an F-type applied part, or in other words, it's going to have conductive contact with a patient, well, what happens if you have an unintended voltage from an external source on the patient and they're connected to this piece of equipment that's connected to them? We need to be able to account for that. Another way to put this is what you might hear as a mains on applied part tests, which, as you can see, I've listed there below. So it's another one of these worst case scenarios that we need to consider when we're doing these measurements. So that being said, I've kind of already mentioned mains on applied part, so let's talk about patient auxiliary current. This one, simply put, is just patient flowing from patient lead to patient lead. I know I used the fancy phrase there from the medical device standard, but if you have two patient leads with two separate functions, sometimes even with the same type of function, if I have both of those things connected to a person, let's say ECG electrodes that have various functions, I want to know between the insulation barrier of one patient lead and the other patient lead, how much leakage current do we have flowing? That's another important metric that we might want to measure. We want to measure leakage current flowing through there because what if there's an excessive amount? We want to be able to measure that. So that's basically patient auxiliary current. That's how I remember it. It's just patient lead to patient lead. And then patient leakage general is just patient lead back to our system reference. Then, of course, we have our mains on applied part. This really is when we're specifically dealing with an F-type applied part, and which I will describe in a minute, which, again, unintended voltage to the patient, through the patient, and then going through an applied part back to an earth reference or a reference point to measure a worst case scenario there. And as you can see, a little footnote there, I took some of these definitions from 60990, which is methods for measurement of touch current and protective conductor current. By the way, if you've never gone through that standard, even if you have other standards that apply, I do highly recommend it. It's a short standard, and it gives a really good detail of touch current, protective conductor current, also known as earth leakage, and just different methods for measuring that kind of stuff. It's very informative, so I highly recommend taking a look at it, even if it might not apply to you. It's instructive and it's informative. And then, of course, the medical device standard. That being said, we're going to do a quick poll here, basically asking you of all the types of leakage current that I'm talking about, which tests do you guys perform? We're very curious to know this because it gives us a good test sample of who's doing what. And I'm assuming since you're attending here today, every one of you is at least doing one of these. Keep in mind for this poll, you can select more than one answer, and we certainly encourage you to. If you do all of them, select all of them. One of the choices is mains on applied part. Keep in mind, I also mean that to apply to external voltage on a signal IO and external voltage on an enclosure point that may not be protectively earthed, which I believe are figures 17 and 18 respectively in the medical device standard. So if you're doing those tests, just count that in as the mains on applied part test when we do this poll. And we will leave this open for about 30 to 45 seconds.
Okay, Nick, we got about everyone who's going to take the poll to take it. The results are as follows. Earth leakage had 85%, touch current 62%, patient leakage 28%, patient auxiliary leakage 21%, and mains on applied part was 33%.
Oh, interesting results with the mains on applied part being greater than the patient leakage current, although I might be able to see why that might happen, especially since I did mention about an enclosure points and things of that matter. You don't have to have a patient lead to have to do, let's say, mains external voltage on an enclosure point or a signal IO point on a medical device that has no patient leads, let's just say. So that does make sense, and that's kind of the distribution I was expecting. Obviously, earth leakage is the most common one. If you're doing patient leads, there's a very, very good chance you're also doing an earth leakage test. So the distribution, that's kind of what I was expecting. I'm happy to hear those results because then hopefully people are the attendees here are going to get a lot of information out of this webinar. So thanks everyone for sharing. Certainly appreciate that, and it helps us help you guys, especially when we're dealing with application calls and things of that nature. So that being said, I did promise that we were going to talk briefly about the patient lead types. I just wanted to talk about these very quickly. I didn't want to blow through this without mentioning what the medical device standard says about these. If you look at these definitions, they're not very terribly descriptive. It doesn't say much, and I did cut some language out of here. There's a lot of text of the definitions in the actual standard, but just to touch on these briefly, the two main types of patient leads fall into what are two main categories here. You got B-type and you have F-type. And B-type is defined as an applied part that provides protection against electrical shock, particularly regarding allowable patient leakage current and auxiliary current limits. And we will go over those limits. We'll take a quick look at the medical device standard and talk about those limits. I like to think of B-type as it could have contact with a patient, but in normal use will not have conductive contact with a patient. So maybe something like a hospital bed, for example. Yeah, it has a motor in it, things move, but normally conductive contact with the patient is not the normal state of operation. So you can imagine that the rules for a B-type would be less stringent than they would for something that is intended to have a conductive contact with the patient. So then we move on to our F-type. Applied part in which the patient connections are isolated from other parts of the medical equipment or medical electrical equipment. That's what ME equipment stands for, is medical electrical equipment, to such a degree that no current higher than the allowable values, which again goes to a couple tables in the standard, flows. And then of course we're talking about this unintended voltage from an external source. So basically what it's saying is, hey, these values can't be above these numbers that we're going to give you in this table, and also if it's an F-type applied part, you're going to need to apply this external voltage to account for the fact that a patient could come into contact with this external voltage while being connected to one of these patient leads. And then that further breaks down into two main types, type BF and type CF. Type BF is designed to have conductive contact with a patient, but is not designed to have direct cardiac contact. Okay, so you can imagine that the rules for that are more stringent than a type B applied part, but not quite as stringent as type CF. And type CF is an F-type applied part, which is designed and intended to have direct cardiac contact. So an example of a type B F-type applied part might be something like an ECG electrode. Yes, it does have contact with the patient, could have contact with the bare skin, but it's not going to contact the heart directly. Whereas like something like a type CF, let's talk about maybe an electrosurgical generator used during surgery, which could have and is intended or could be intended to have conductive contact with the heart. So you can imagine that type CF are the most stringent limits when we're dealing with leakage, because obviously you don't want much leakage to be contacting somebody directly through their heart. It would definitely be a bad thing. So just keep these in mind as we move through the presentation. Again, I'm sure you guys listening have heard these definitions. Some of you are probably very familiar with them, even more so than I am, but I think it's important to mention that. So when we're talking about leakage current, and this is kind of jumping back to the previous presentation, but I want to quickly mention how it's measured. It's measured through what we call a human body impedance network known as an MD. So when we're looking at some diagrams today, if you see a little MD with a square around it, that's the measuring device, and it's basically designed to simulate the could be exposed to. So we measure under the normal conditions, the single fault conditions, and then we determine, do they go over the limits that the standard says. If somebody is exposed to these conditions, these worst case scenario, at elevated voltages, is it going to be a problem? Is it going to pose a shock hazard? Is it going to go over the limits that the standard says? That's basically what it comes down to. Just to look at some measuring devices, here's what we have for several different standards. Obviously, we were talking about medical device. That's in the upper left-hand corner. By the way, these images are taken from the LCD display of our Omnia tester that you will be seeing later in the videos. It includes, as you can see, various networks for measuring leakage current, medical device included, as well as IT equipment and electric spas. One common theme you'll notice here is it's usually a series of resistors and capacitors in which you're measuring the leakage current through. Reason being is you want to incorporate a frequency response curve when you're talking about this, because as frequency increases, as with any response curve, there's going to be a bend and there's going to be a different physiological effect when you're talking about different frequencies. I believe the medical device standard has you go DC up through 1 megahertz for a response curve. So that's important to note. That's why we have caps in there, because it's not just a straight up resistor. You're not just measuring leakage current like you would during, say, a dielectric withstand test. That response curve has to be taken into account because it more accurately models human body impedance. So let's take a look at a quick circuit example. Here's, let's just say I was running a leakage current on a fan. Probably not the best example for leakage current, but it'll do. If we break that down into a circuit, basically what you see there on the left-hand side, you have mains voltage coming into the instrument, passing through it, and then passing out to that little adapter box that you can see right there. That's what we see where the fan is plugging in. That's what we call an adapter box. So you plug in, you're feeding voltage from an external supply through the instrument to power up the device under test. As you can see, there's the little MD symbol so that we can take our measurement. So just imagine we're plugging in our DUT and we're running the product under normal conditions. Right? So as you can see there, there's really not much, if any, leakage current flowing through the MD. Why? Well, switch S3 there, your ground conductor, it's closed. So if there's any stray current, it should really be going through the ground conductor, not through somebody who may be, say, touching the enclosure of the fan or the medical device or whatever the case is. Switch S1 is, we can see, is our neutral switch, and switch S2 is a polarity switch. So this represents the 3 switches that we have in our Omnia instrument. For anybody out there who might own other types of leakage testing instruments, you may have other switches in there as well. This is the ones that we utilize. These are the most common ones you're going to run into, and they'll cover the vast majority of your testing cases, but you again might have others. So of course, if we open our neutral, that's considered a fault condition. If we reverse our polarity, in some standards that's considered a fault condition. In the medical device standard, it is not. And you can see still not much going through our MD, if anything at all, because our ground is closed. But once our ground is open, then you're going to get leakage current through the DUT going back through the MD to measure it. And if you ever have run leakage tests before and you compare a closed ground to an open ground measurement, it's not uncommon to see the readings go way up. I just ran a test the other day on a customer who sent a DUT in for testing, and I believe when it was normal conditions, the leakage current was like 0.5 microamps. As soon as we did an open ground condition, we were up in the 150 microamp range. It's pretty common to see something like that. So before we really dive into some tests, let's go over what the 60601 medical equipment standard says with regards to leakage current. So 8.7 leakage current and patient auxiliary current, or also the touch current test, the requirement is tested in normal condition and single fault condition. The other requirement is that we are testing with a supply that is at 110% highest rated mains voltage, i.e. if the highest rated mains voltage on your product is 120 volts, you're going to be testing this at 132 volts. If it's 240 volts, you're going to be testing at 264 volts. Again, worst case scenario situation. You're also testing at the highest rated supply frequency, meaning if your device can handle 50 and 60 hertz on the input, you're going to be testing at 60 hertz. So let's just say you have a device that can handle anywhere from 100 to 240 volts, 50, 60 hertz. You will be running these tests at 264 volts, 60 hertz. Worst case, highest voltage, highest frequency. And then for earth leakage, which we kind of talked about last time, but I'll hit it on here real quick. For normal conditions, you got to be less than 5 milliamps, and for single fault, 10 milliamps. For touch current, it's 100 microamps normal condition and 500 microamps single fault condition. And then for patient leakage current, we are going to be looking at tables 3 and 4, which we'll look at here in a minute. Now we're going to drill down here even more. You'll see the bottom section of this actually breaks it down because there are more than just these tests. We already kind of talked about this, but it gets very specific when we're getting into section 874 for leakage current measurements. The touch current measurement's pretty straightforward. We're actually going to be looking at that figure and an example. And then if we're talking about patient auxiliary, that's actually pretty straightforward as well. We're just measuring patient lead to patient lead, but when we're talking about patient leakage, we could be dealing with several different types. We could be talking patient lead to earth, which is figure 15. Mains on applied part for F-type patient leads, figure 16. Mains on a signal I/O port, figure 17, and then mains on non-protectively earthed chassis point, say that 5 times fast, figure 18, which we're going to look at several of these figures. So we're looking at a lot of different scenarios here. And if you have a pretty complex medical device, you could be dealing with all of these. Jim, are we still good? I just got a little message here that we may be getting some network difficulties.
Everything's fine on my end, and I've not seen any kind of feedback negatively. So
okay, just making sure. I just got the GoToMeeting just kind of popped up a message here, so just making sure. All right, so moving forward, you can certainly keep this in mind. By the way, I took these selections from, basically we created a standards cheat sheet. You can get it directly off the AR website, and obviously this was taken from the medical device standard, but what this thing was designed to do is I have various standards listed, including this one, 61010, 60950, 60335, some of what we call the big standards that we deal with, and not only does it tell you the specific requirements and sections, it tells you the requirement, the pass criteria, and which of our units, which of our instruments you can use to meet these criteria. So it'll give you kind of point you in the direction of which units to use, and it also tells you basically what we can't do. You know, our units don't cover everything, and we get a lot of questions from customers that basically say, hey, I'm testing to this standard, can you meet these section requirements? That's what this document is designed to help you do. So I urge you to take a look at it if you ever have questions along those lines. You can download it directly from our website. So moving forward, patient leakage current. Let's look at some limits here. Fortunately, I have the standard that we can take a quick look at here. So this is table 3 for allowable current limits for patient leakage and patient auxiliary and normal and single fault conditions. So you can see there's pretty wide range of limits. You'll also note they separate this out into AC and DC, meaning that if you filter it and measure DC only, you'll see the limits are a lot lower. And then, of course, there's the AC. By the way, with a lot of instruments out there, and ours included, on our units you can actually filter it. You can choose AC, DC, or composite, which is just everything, AC and DC. The composite waveform limits and the AC limits that they show on this table are the same thing. So if you're measuring with a standard one, you're probably following the AC numbers rather than the DC, but you certainly can filter to DC and use the other values as well. So you can see pretty much what you have here is it goes from type B to BF to CF, and it's not surprising that when you get to CF, the limits drop drastically. As I mentioned before, much more stringent than you would be dealing with the type B or BF type applied parts. But it pretty much ranges from about 10 microamps on upwards to about 1,000 microamps. So the limits for patient leakage, you can see, are much lower than your touch current, well, not necessarily touch current, those are pretty much in line with these, but your earth leakage current. Earth leakage current, you're talking about 10 times some of these values. Remember, it was 5 milliamps normal and 10 milliamps single fault. And it makes sense. I mean, earth leakage current is technically a measurement of leakage current on your entire system, so those values are going to be higher. Sorry, I had to take a sip of coffee there. So we're dealing with several different types. We've got patient auxiliary, patient leakage current for patient connection to earth. That's what we would just call general. And then patient caused by external voltage on a SIP-SOP. External voltage, SIP-SOP being signal input, signal output. And then, of course, you can tie these parts together if they have a similar function. We're not really going to delve into that too much. Most people I've ever talked to who design medical devices that are doing this testing, they know when and they can and cannot tie a patient lead together. Generally, if they have the same type of function, you can usually tie a bunch of patient leads together and do the measurement. It's going to save you a lot of time on testing, but in some cases you can't do that. So it's really up to the manufacturer's discretion on when they need to do that, but it is described in section 8.7.4.7 if you want to take a look at that in standard. And then really quickly on table 4, this is where we're talking about allowable values for these more specific tests. So now we're really looking at more like the mains on applied part test, because we're talking about an external voltage on a patient connection of an F-type applied part, or possibly something that is not protectively earthed, which with regards to running the test on a unit, even though the measurement will be different, it's kind of the same test to run. It really just depends on where you're applying your points. So, not to hang too much on this particular slide, let's take a look at touch current, 60601 figure 14. Let's take a quick look at the diagram and get a feel for what we're talking about here before I show you guys a video example. Now I want you to ignore the top half of that for a second. Let's just look here. On the left-hand side there, you're going to see T1. That's just transformer 1. That's your power. That's your 110% mains voltage that I had mentioned before. So you're running that through your leakage network, which you can see the voltage is being measured by a voltage meter there called V1, and then you have your various switches. So if you have a leakage tester, the switch S1, the switch S5, the voltage measurement, maybe switch S7, certainly the protective conductor switch for S7. These are all being handled internally by your leakage tester. And then on the right-hand side there is our DUT. It's the medical device. So, and then you can see we have various points at which we're taking the measurement, where you can see the MD, we're taking measurements depending on the piece of medical equipment. So you can see an MD there between the enclosure point and the reference point on the left-hand side, and then you can see there's another MD there. That would be a measurement between two enclosure points that are isolated and non-protectively earthed. So that could be another measurement that you might have to take. As far as the leakage tester is concerned, it's all the same. You're just referencing different points, and it's taking a measurement using that MD. And additionally here, you can see we have T2, which is an external transformer. Now, what I kept mentioning in previous slides, unintended voltage by an external source. This is what I'm talking about. This is another 110% external voltage run through, and in this case it's going through to the signal input, signal output. That's what 3 there is labeled. So if you have a SIP-SOP that you have to account for, you may have to apply an external voltage and then take these various touch current measurements. Alright, so let's take a look at a couple examples here. Some videos that I set up that hopefully are informative to you guys. I have several of them here, so bear with me. I am not a professional video taker, and I have a few of them. I chunked them up. So the first one we're going to watch here is just the connections that I'm making. I just want you to understand what I'm doing. You may not have used our equipment in the past, so I think it's important that I lay that out. So what you can see here is I have connections from a power supply. So what we have here are line, neutral, and ground connections. We also have our probing points, probe high and probe low, depending on what measurements we want to take. So that's linked up. Line, neutral, and ground are linked up to what we call this universal adapter box. So we have L, N, and G right there, so I can just plug in the equipment. And then we have our 2 probing points, which just terminate in some clip leads, so that we can get a nice grip on an enclosure point or a patient lead or something like that. All right? So keep those connections in mind as I go through and I show the next video. I skipped one. There we go. So now what I'm going to do is actually set up the test. So first I'm going to turn this particular unit. You'll see what I just did there. I'm just going to turn that back here for a second, guys. Let's go back for a second. I wanted to show you guys something. You'll see that I went into the hardware and I turned on the AC source. This particular instrument actually has a built-in 500 VA power supply. Most leakage testers don't. If you don't, you have to use an external supply of some type, but that's why I did this. I wanted to show you that I'm enabling an internal source, because some of you may have been confused thinking, hey, what source is he using to power up the DUT? You'll notice I didn't have anything additional plugged in to the unit, and that's why. This one has a built-in power supply. So now I'm going to go and I want to set up a couple tests just as an example here. I'm going to set up some line leakage tests. I'm going to do a touch current test with 1,000 microamp high limit. I'm going to set a couple voltage limits, and you'll notice here I'm just running nominal voltage. I could obviously run like 132, but what I did was I'm running nominal voltage and I have a high limit of 125, meaning I don't want my voltage to go over that number. I also don't want my voltage to go under 115. I'm going to set a dwell time of 5 seconds. a delay time of 5 seconds, delay time just being allowing some time for the equipment to power up and get into a ready state before I make a determination on pass-fail. I'm also going to look at some fault conditions here. You'll notice we have our neutral, our polarity, and our ground circuits. I also have the measuring device for 60601 selected. And since I'm doing a touch current test, I don't want to do protective conductor current. That would be for earth leakage. So this is essentially the network we're dealing with. If you look on the right-hand side, you'll see where the MD is being placed. And right now, it's going from ground to line or ground to neutral, depending on your polarity. That would be measuring earth leakage. I don't want to measure earth leakage. I want to use a probing point. So now you can see I selected probe high to line, and now we're measuring from our probing point, i.e. whatever I contact, back to our system reference, and I will be contacting an enclosure point for touch current. I also want to make sure I'm setting my power supply, which is internal, so it's one of the parameters. So I'm setting my voltage source to 120 at 60 hertz, and I don't have a specific high limit set. Go back. Let's add one more leakage test with a fault condition, and I'll open ground in this particular case, and you'll see that right there the ground switch opened up, showing us that we're doing that. So I'm going to go ahead and save my settings. And then in the next couple videos, we'll show how we do this test. So let's look at the next one. And let's look at my setup here. Now what I have is, you'll see I have my Omnia instrument. And in this particular case, I'm using the example of a PC. And you might be wondering, what the heck is he doing here? Well, first of all, I have this PC enclosed in a little enclosure for safety. It's isolated from everything. That's a plexiglass enclosure. And any metal components on that enclosure are grounded out. You'll also notice I have a PC and what looks like a big foil block. That is a big foil block. It's actually foam with foil around it. And what I'm doing here is I'm placing it over the keyboard. I actually got this idea from a customer of ours. They had a medical device that had a PC and a keyboard that the operator had to punch in commands to the device. So what they were doing was they had to test for leakage current to the keyboard because the operator was going to be touching the keyboard. So what they did was they took a piece of foam, they made it completely conductive by putting foil around it, and then they put the foam on the keyboard, which I thought was a pretty neat idea. So I'm doing the same thing here. I borrowed their idea. So here's the conductive point, and there's my probing point. You know that probe high point that I selected? Well, there it is. So I'm measuring probe high back to system reference to get a leakage current value. So that probe goes into the rear panel of the instrument like I showed you before. So that's basically our setup here. And then let's run the test and see what kind of numbers we get. And for this particular example, it's a laptop, a class 2 device, so we're getting minimal leakage current in both normal and single fault conditions. So I was expecting pretty much a value like this, and that's what we're seeing here. So obviously the test here is going to be a pass. But again, I just wanted to show you guys an example of what you might do for a test like this. It's pretty simple. I mean, really all you'd have to change here, as far as the instrument's concerned, as long as you get your probing point on the right spot, doesn't matter if it's going to a patient lead, a foam block with foil on it, saline solution you might be using to make conductive contact, which it talks about in the standard, it really doesn't matter from the standpoint of the equipment. It's just taking a measurement from point A to point B. Patient leakage current. Sorry to keep bouncing around here, but I really want to do this by looking at the actual standard and seeing what we have here. So now for the patient leakage current, and this one is actually, I believe, yeah, this appears patient leakage here. Pretty simple diagram, actually. As you can see, you see where it's labeled 4 on the diagram, but that's a patient lead. So you can see what they're doing here is they're tying the patient leads together, and that's one side of the MD, and the other side of the MD is our reference point. As you might imagine, as far as the testing scheme is concerned, this is really no different than the test I just ran. You have a probing point on one side, you have your system reference on the other, and you're taking a measurement. So keeping that in mind, let's take a look at an example here. Now, I didn't want to use an actual medical device on this one. I'm just going to use one of our pieces of equipment as an example just for various reasons. But it's still going to give you a good idea of what we're talking about here as an example. So let me set up a separate test for this one. We're going to set up a patient lead test. I'm changing my high limit to 500 microamps. Keep my voltage the same, keep my other parameters the same. That's not going to make a difference in this case. I'm going to go normal conditions for my 500 microamps. And you'll notice I'm going to keep the same MD. And my probing point's going to be the same. As I mentioned before, probe high to line. Don't need to change that. Now you'll notice in this video that I did have a composite measurement, AC plus DC. So once again, now we're going to introduce a single fault condition, and we're going to up the ante and increase the leakage current value a little bit, as you're allowed to in the standard. The limits I just set were actually for a touch current test, but in this particular case, I would have actually, in most cases, used 50 and 100 microamps, but 500 and 1,000, 500 and 1,000 would actually work for a patient lead too, for a standard patient lead. So in this case, here's what I did. Let me play the next video. You'll see in the enclosure here we have our simulated medical device, quote unquote, and I used one of the connections to simulate a patient lead. So you see I used that terminal coming out of the device there, and I connected that directly with our probing point. You can see I have the device plugged in, so that will power it up. And so essentially I'm simulating a patient lead with that probing point back to our system reference. Pretty simple, and it's very similar to what I just did. So now let's run the test. So you can see we are powering it up and we're getting our measurement. One thing I want you to note here is that we are doing normal conditions. That's what my finger's pointing at. You can see we have our probe high to line or our probe high to neutral depending on the polarity. This is actually probe high to neutral, which is our reference in this case, which is correct per the standard. And then we have normal conditions, and we're not getting much of a reading. As I mentioned before, your MD is being shorted out by your ground connection, so you're not going to get much of a reading. But as soon as I flip and do an open ground, you're going to notice a change. Went up a little bit. And then back to an open neutral with a closed ground. Pretty low values. Again, I'm just connected directly to a probe on one of our items here, but you could do the same thing with a patient lead. It's pretty much the same test. You'd set it up exactly the same on the Omnia. Now, patient auxiliary, as I mentioned before, let's jump down to figure 19. That's your patient lead to patient lead test. All right. So pretty straightforward. All we're doing is replacing the MD between two separate patient leads. We want to measure the leakage current through that insulation barrier, simply put. But I'm going to need to change it up a little bit with regards to my test, because now I need two probing points, not just the one probing point in the system reference. We're dealing with a little bit of a different situation here. So I'm going to keep my limits, but I need to change from probe high to line to probe high to probe low, because now I have two probing points. So I'm going to go through, and I'm going to keep my same limits, which technically if I was doing a medical device, I would change those because patient auxiliary can have slightly different limits. They could technically also have the same limits, but now I'm just going between two probing points. So I'm placing the MD between two patient leads. And I'll go ahead and save those changes. Now you can see what I did here is I just used two different points on this device to simulate two different patient leads. So now you can see I have probe high and one patient lead, and then probe low right here on the right and another patient lead connected to the black one, simulating patient lead to patient lead. We're still plugged in. And now let's go ahead and run a test. Once again, normal conditions. Getting nice little numbers there now that we're actually going across some components in the instrument, and that's why we're definitely seeing higher readings than we did in the last test. Now we open the ground, get yet another reading, and then back to an open neutral condition. And it drops considerably as the device is powering down because we opened our neutral. Great. So I didn't want to dwell too much on that because there is a video I want to show you guys that for mains on applied part. I know a lot of people asked about that, so I do want to get to that. And it's like a 10-minute video, so I want to make sure everybody understands that. Now let's take a quick look at figure 16 for our mains on applied part test because it looks really tricky, but it's not tricky when you look at all the components here. So what we have here is you're going to see this looks very similar to our patient leakage test, right? We have our patient leads on one side, but now instead of just simply going to a reference point, we are going and applying this external voltage shown by T2 through switch S9, and you'll notice switch S9 is also a polarity reversal, through a resistor labeled R. By the way, that's an optional resistor, and it's a resistor for operator protection when running this test. And I do use that in my video. So on one side, we have an external voltage that the patient could see, an unintended voltage at 110%, also considering a polarity reversal with switch S9. And on the other side, we have our patient lead. And under these varying fault conditions, we want to measure what's going on. So let me jump over to this final video. It's actually, I posted it on YouTube, and here it is here. And I'm going to go ahead and play this. And I have audio on this actual video, so it won't be me talking, but we did a test yesterday. The audio should come through just fine.
Line leakage testing per the medical device standard for running earth leakage, patient leakage, enclosure leakage, patient auxiliary leakage, and mains on applied part testing. Today I've provided a simple example showing how this can be done. What I'll be using today is the AutoWare 2 software, which we use to communicate with the instruments, as well as an Omnia
Nick, I don't mean to interrupt, but I think we lost audio on the video.
16-channel
How's that?
and here I have an 8-channel slave.
Better.
How's that?
Better.
To the software and showing you what the parameters are for each step. I'm just going to briefly show you what I have here for this particular demonstration. So there's a lot of wires going on back here, and hopefully you can see this without too much difficulty. Basically what we have here is a medical device with 4 patient leads. And I have the 4 patient leads connected here. You can see I have 3 patient leads connected here and the 4th here. Those are going back to the master channels 1 through 4, patient lead 1, 2, 3, and 4. I also have a protective earthing connection from the medical device, which is going here into channel 8 on this master scanner, as well as channel 3 on this slave scanner. And I'll explain in a moment why I'm using 2 scanners and why I have 2 PE points. But I basically just wanted to show how the patient leads are connected so that we can run this in an automated sequence. Additionally, what I have is I am using a linear 1 kVA power source to simulate my T2 or my transformer 2 for my mains on applied part testing. So what I have here is 132 volts going through these lines, and you'll have to forgive me, I don't have professional fixturing here, but what I have is line and neutral. I paralleled them, and I'll show you why. This also explains why we have an extra PE connection. I have line and neutral going to these 2 scanner channels, which are 6 and 7 on the master scanner, and then PE goes to channel 8. And then I additionally also have line and neutral going to the second scanner, as well as PE going to channels 1, 2, and 3. The reason is because if you look at the standard and the way these tests are run, you actually reverse polarity at some point from T2. So here we can see T2 and we have line neutral going through a resistor, through the measuring device and back up to the patient lead. Well, at the same time as running line through this resistor, I need to tie neutral in to my protective or reference point. So by putting them through two separate scanners, I have the capability of tying these points together without including it in the measuring circuit. So that's why I've used two scanners in this instance, essentially to provide isolation. So what I'm going to do here is put the camera in the mount and run through a sequence of tests for this demo. So what you're seeing here is actually the AutoWare 2 program. And this is how I set up the tests. A little easier than doing it manually. So I've already created the line leakage sequence, as you can see here, with multiple steps. Now, I'm going to double click on this to show you the various parameters that we're looking at. Now, this is showing me all the parameters I have set up for this test. Now keep in mind this is a demo, so I've kept the limits here pretty much the same across the board for all these tests. I have a 6,000 microamp high limit, 0 microamp low limit. I set my voltage high limit to 135 because, as you can see, for this particular medical device, I'm running 110% mains, which is 132 volts. And I set the internal power source on the device to 132 so that it can run the product at that voltage. I set my voltage low limit to 129 just to make sure that my source is working properly. If it happens to dip below that, I'll get an error message. I set my delay and my dwell time both to 1 second. We'll keep it short. And I have my probe configuration set ground to line, which means this is an earth leakage test. I have the 60601 measuring device, and I'm measuring RMS, and I'm measuring a composite signal, AC plus DC, although you do have the capability to use filtering to measure AC or DC only on this particular device. We also here have our fault conditions, our neutral, our ground, and our reverse fault condition, and our continuous run, which basically will keep the product powered up, of course, given that you don't have an open neutral condition, in between steps. Given that this is an earth leakage test, we currently don't have any of the scanner channels set. So that's actually what I've done for these first 8 steps, because if we consider all 3 fault conditions for earth leakage, that takes us out to 8 steps. So on the 9th step is where I actually start doing my patient measurements. Now, I didn't do 8 steps individually for each patient measurement, but when you see how I'm doing this, you'll get the idea behind what I'm doing. You can certainly extrapolate and do as many tests as you want in as many patient leads. Now recall, on my master scanner, which is what I have set here, my SC6540 address 1, I had patient lead 1 connected to channel 1. So I'm setting, with red here, patient lead 1 high. Green is low. So I'm setting patient lead 1 high, and I'm also setting channel 15 high. And if you recall, I set my probe high to channel 15 and my probe low to channel 16. Those probes are simply coming from the Omnia, and they're just probing points that the Omnia uses to reach out and go across various points so that the MD can get a solid measurement. So once again, I set probe high to channel 15 and probe low to channel 16. Since I'm just doing a patient leakage test here, I'm only selecting my probe high to line configuration because I'm measuring patient leakage back to the line or neutral reference of the system, depending upon the polarity switching while you're running these tests. As you can see, I'm still running 132 volts, and I still have continuous on. And basically all I have here is I have my probe high, which is, again, connected to channel 15, going out to short to patient lead 1. So I basically simply repeated this process for patient lead 2. As you can see here, now I have patient lead 2 high connected to probe high, which is on my channel 15. For the next step, I have patient lead 3 high connected to probe high. And then finally, of course, I have patient lead 4 high to connect to my probe high. So that pretty much takes care of showing what the patient leakage is all about. And we have a few more steps here. 13, 14, and 15 outline patient auxiliary testing. So now what we have are very similar parameters as you saw in the previous steps. However, you'll notice I've changed my probe configuration from probe high to line to probe high to probe low. So now I'm using 2 probing points, much like you'd use with a multimeter if you were just taking 2 probes and going across 2 points. with the 60601 measuring device, and I have patient lead 1 high set to probe high, and patient lead 2 low set to probe low. So essentially, we're just measuring from patient lead 1 to patient lead 2 while the product is running at 132 volts. And I repeat this process for the remaining steps. Now I'm going from patient lead 1 to patient lead 3, still keeping probe high and probe low in the circuit. For step 15, I simply am taking patient lead 1 to patient lead 4, probe high to probe low. Now for steps 16 and 17, this is where I illustrate the mains on applied part test. Recall that I brought line neutral and protective earthing to both scanners so that I can complete the circuit at the same time providing isolation. So I'm still on a probe high to probe low configuration, only this time I've got channel 6, which is line voltage. This channel here is line voltage coming from the isolation transformer T2 connected to probe high through that resistor. And then I've connected probe low, channel 16, to patient lead 1, which is on channel 1. So that takes care of the measurement circuit for probe high to probe low through the MD on the mains on applied part. However, I still need to complete the other side of the circuit. So on the slave, I've tied channel 2, which is neutral, to the protective earthing point, or our reference point, shorted together to complete the circuit on that side, but at the same time, now it's not involved with our measurement. And I've simply now repeated this process for the next step, but now I've reversed the polarity of the lines coming from transformer 2. So now I have channel 7 high, which is the neutral of the circuit, in contact with probe high, and channel 16, which is probe low, in contact with patient lead 1. And then we'll see on my other scanner, now I'm bringing line voltage from transformer 2 in contact with the PE point and tying those together as it would be exactly on the diagram for figure 17 for a mains on applied part test. You can well imagine you can extrapolate this out to as many steps or patient leads as you see fit, given that you have enough scanner channels to run this test. So I'm going to go ahead and save this information and jump over to my control panel. Now here you can see that the Omnia and the program are working together to load all the files onto the unit. Once it's complete, I'll be ready to test. So I'm going to go ahead and push the test button and we'll watch it run through the sequence. So what we can see here is the Omnia running through the test. We can see the voltage. We can see the leakage current measurement. We can even see the fault conditions here. Currently we're on step 4. Here's step 5. So we're still on earth leakage, and we can still see we have a G to L probe configuration here. Step 7, step 8, and now step 9 we're going to start going through various patient leads. So here we can see probe high to patient lead 1. Probe high to patient lead 2, and remember probe high is channel 15, so that's just connected to patient lead 2 here. Probe high to patient lead 3, as this LED goes on, still connected to my probe high. Probe high to patient lead 4. Then we go into our patient auxiliary tests after this one. So now we can see patient lead 1 to patient lead 2, probe high to probe low. So we have our probe high, probe low here. Now we have patient lead 1 to patient lead 3. And finally, patient lead 1 to patient lead 4. Finally, we have our mains on applied part tests. And here we can see getting a little more leakage, only about 1 microamp in this case. But now we have probe high to probe low, line voltage connected to probe high, which is channel 6, and probe low connected to patient lead 1. At the same time, on the other scanner, I've shorted my neutral to my protective earthing point because I've tied those points in there. And then finally, on our last mains on applied part test, I flipped the polarity of this circuit. Now we have neutral connected to probe high, probe low connected to patient lead 1, while line voltage and PE are shorted together on the medical device. You can actually see it powered up here doing its thing. And the test sequence has completed. Now, of course, were this an actual run of tests that I was going through, we'd have many, many more steps. We'd have 8 steps for each one of these conditions. But I wanted to illustrate here.
All right. So I think you guys get the point there. So that was a long video, but I know I repeated some things in there, went through some tests we already talked about, but it was a little bit of a different setup, and I wanted to show that anyways because I think that could be helpful. So I know we're coming short on time here. This is just a quick recap of some of the stuff we talked about for mains on applied part, external voltage on signal input output, and external voltage on a PE part that is not protectively earthed. Point being that if you're using a leakage meter, those 3 tests, as far as using a scanner or otherwise, you'd pretty much run the same sequence. It's just the probing points that are going to change. All right? So that being said, I know we went through a lot of info today. I kind of had to speed through some of it just to show that video. But if you'd like a copy of the presentation, let Jim know. Check out our website, and don't forget to follow us on YouTube, LinkedIn, and Twitter. We always have updates about these types of webinars, my various YouTube videos I upload about application examples, new products, stuff that could be very helpful to you, and that's all free to do. I really appreciate everybody's attendance here today. I hope you guys got something good out of it. I'm going to leave the floor open for a couple minutes for questions. If it's a question that is going to be really in-depth, please email us, info@asresearch.com, and we'd be more than happy to discuss in more detail. But once again, thank you, and see you at the next webinar late October. Well, I don't see much in the way of questions. Do we got anything, guys?
No, I was just logging on. Doesn't seem like there's anything to address. For all those who are still with us, if you do have questions, just shoot them over either info@asresearch.com, or you can send them to me directly, Jim K @asresearch.com. And we also have all these questions logged, so we can also come back and sneak a peek if necessary. So just want to thank everyone for attending. Nick, I'll let you go ahead, sign off, and then we'll see you guys next time.
All right, thanks, Jim.